Very warm welcome for everyone on this beautiful evening for this today's session. So today, before we discuss about the main objective of today's meeting, if we recall what we have discussed on previous session and the earlier session, mainly we have discussed on two topics. The first one is on programming model, where how to create as many number of threads we want and write kernel definitions and say that, oh, these threads should go and work on these instructions. This is what primarily we have discussed on first class of this particular module. And in the second class, again, we looked at essentially on previous class, we have discussed about the concept called memory coalescing, where one of the main objective of this memory coalescing is to reduce the number of global memory transactions, because global memory is not within GPU card, it's just outside. I mean, in the GPU card itself, you look at the distance or in terms of the actual locations. It is not considered to be on-chip memory. It is considered to be off-chip memory. So global memory accesses are always expensive, and try to reduce them and try to in a sense where all threads within a warp, those 32 threads, is better to access all consecutive memory locations and so on. That's what we have discussed in previous session. Now let us continue on thread programming, where again we discuss on uh, essentially within a warp, those 32 threads, how are they doing computation? The computation part today we are discussing, whereas on earlier session we have discussed on the transfers between global memory and cache. So in today's session, primarily we start working on few programs on how do we handle 2D arrays. Then the major concept is on thread divergence. This is the main focus on today's session. Then further there is a small topic on atomic operations, and of course we will be able to see that there are some programs with and without thread divergence. So the main focus is essentially how do we minimize thread divergence. This is what the main theme of today's session. So let us look at this programming question. So the very similar programming question what we are discussing now, we have seen on first day for one-dimensional array. Now we are discussing about two-dimensional array. Given a two-dimensional array like A of 2, 5, which means we have 2 rows and 5 columns. Total we have 10 elements. Now what is the goal of this the programming question? We need to increment all the given numbers in the given array, right? All the numbers by 1 in the given array. This is the programming question. So if at all there is something like 5 is there, after we increment, the 5 should become 6. This should happen on all the cells. This kind of program is very easy to write on one-dimensional arrays. Of course, in two-dimensional arrays as well, this is very similar to that, but there are few concepts need to be understood before you go to the next steps. Yeah. So if you look at typically we declare like this A of 2 of 5, right? A of 2 of 5. This is meant for declaring a two-dimensional array, which consisting of the first number indicates the number of rows, the next number 5 denotes the number of columns. This is very natural. You all must be familiar in C language and many other languages. So this is very natural. Now let us come to how do we declare the corresponding number of threads, right? If we have 10 threads, sorry, if we have 10 elements, now we need to create 10 threads, and there should be a one-to-one mapping between this thread and the corresponding element, right? So of course you know the dim3 data type and the number of threads per block. We want to give something like 5, 2. What does this mean? Here you have to pay a little more attention that the first parameter 5 denotes the number of threads to be created in x direction, right? 0, 1, 2, 3, and 4, right? The number of threads need to be created in X direction is specified as a first parameter. In the second parameter, the value whatever we specify in the second parameter denotes that the number of rows, right? This one denotes the number of rows, or in some sense number of threads to be declared in to be created in Y direction. So the first one is for X and second one is for Y. This you have to be very careful, because here we are declaring 2, 5, but whereas here we are not declaring 2, 5, rather we are declaring 5, 2. So you have to pay very much attention on that. Otherwise, if you declare 2, 5, then the number of threads will be like this, right? So we have to pay attention on that. Now let us go and understand what is the main task that we need to assign for each of these 10 threads, right? If you look at this thread, the responsibility of this thread should be, this thread should go and access this element, the element available in this position, and increment by 1. Right? These are indices numbers. This I am calling 0, 0, 0, 1, and so on, right? Now, how do we do that, right? So when there is a small confusion people typically do, where when you are assigning this thread index dot x and y to column and row, or row and column, if you interchange that, there is a lot of danger, right? So you have to be very careful in this. So let us go little more slowly. So look at this thread. For this thread, what is the x value and what is the y value? For this thread, x value is 2 and y value is 1, right? So many times, rather than trying to understand as a x value, y value, or I value, j value, in arrays we talk about I value and j value, right? Which means I stands for row and j stands for columns. So here on threads we talk about x direction and y direction. So rather than thinking of all this, if we fix row and column are very clear, either in arrays or in threads, right? So what is the row number for this? For this thread, row number is 1, and this we should be able to obtain using y value, right? So look at here, right? For this thread, the thread index in y direction we are storing in row. Again, similarly for the same thread, you look at x direction, this value tells us column number, right? So that is what we are doing in these two lines. Please pay attention. I'm giving half more or possibly few more seconds. Please work on this slide one more time, right? This thread index x value is 2. What does this mean? This is column, right? This thread value is 2 for this thread, and this value refers the column number, this column number. Similarly, for the same thread, there is a 1. This 1 is going to tell us y value, and y value is referring to row. So which means if lot of threads, all the threads are executing this instruction, this sequence of instructions, right? Then the corresponding thread, this thread whose row number is 1 and column number is 2, is going to access an element from this two-dimensional array whose row number is again 1 and column number is 2. So which means we are able to establish this mapping. Once you establish the mapping, then everything is very crystal clear, where in a sense that Tij is going to access an element in the corresponding element in array and increment. That's what such kind of program one can typically write. But there is one more small incremental version what you can think of. So if you follow this approach, the approach what we are discussing in this slide, we have created enough number of blocks. But within a block, we all know that 1024 is the maximum number of threads that we can launch. So the total number of elements in your array is more than 1024, then we cannot compute the final result using one single block. So we have to go for multiple blocks. right? That is the reason now we are trying to increase the number of blocks. This is one block, this is another block. Similarly, we have 4 blocks. In this example, I am just going for 5 comma 2 and 2 comma 2. Of course, it depends on the number of elements in your array. You should be able to do all this, right? This is the given 2-dimensional array. Total number of columns are 4, and total number of total number of rows are 4, and total number of columns are 10, and total you have 40 elements. Now what is the task? If you want to handle all these 40 elements, you need to have 40 threads. Of course, in this small example, if in this small example is concerned, you can create all these 40 threads within single block. But I am just imagine that the number of elements are more, and in such cases you have to create multiple blocks. Within each block, if at all you want to handle 1024, then in one direction you can handle 32, and in another direction you can handle 32, so that you can get 32 multiplied by 32, 2 power 5 multiplied by 2 power 5, you will get 2 power 10. So 1024 threads you can handle within a single block. All that is possible. For the time being, you can just focus on 10 threads per block. Now, how do we handle this mapping, right? This block, you look at this block. This block should increment all the elements available in this block, right? This block is I mean, if you look at the elements in an array, there is nothing like a blocks, right? There is a single array, but we are virtually thinking of dividing the whole array into multiple blocks and then assigning these mapping between threads and as well as the corresponding elements. You look at this thread. This thread is supposed to work on this element, right? So now if you want to do that, so you need to identify what is the row number for this thread and column number for this thread, right? What is the row number? You look at the row number for this thread. For this thread, what is the row number? This is 0, this is 1, this is 2, and this is 3, right? So for this thread, how do we identify the row number? Using this expression. This expression we have already seen earlier. Many times we have seen this, right? Where we talk about how many number of blocks are there before to the current block, and how many number of threads are there within each block, and within the current block, how many threads are there before my thread, and so on. Using this expression, we should be able to identify the total number of x index or the row number and column number. As of now, we have identified a row number for this thread. Now let us identify the column number. This is 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, right? So we have identified that for this particular column, for this particular thread, the column number is going to be 7. So how do we identify? Very similar logic, right? So as long as you remember that x index will be helpful for column and y index will be helpful for row, done. We are in a very good shape, right? So once you identify this r and c values, a of row and column, the corresponding thread is going to work on the corresponding element and increment. This is as simple as this, right? In this parallel programming, many times we work on this indices and mapping. Otherwise, the computation will be much lesser than CPU, because in CPUs we have to go through all these elements in a loop, whereas in GPU, many threads are working on each item and each thread is working on each item. So which means the computation, the code will be very less. Only the mapping we have to understand much more clearly. Now let us look at the actual program, right? So this is the kernel program. Of course, for the time being, you think of some number of blocks have been declared and some number of threads have been declared and so on, right? Where you know all these syntaxes earlier, where within each block we have 5 rows and 5 in x direction and 2 in y direction. All that we have discussed. And number of blocks per grid. As of now, for this example is concerned, we are following this pattern, but depends on the kind of number of rows and number of columns in your data. You should be able to figure out appropriately, right? But in general, as I mentioned, number of threads per block can be 32 by 32, so that you will be able to get 1024 in within a block. So for this example, I am working on 5,2, but in general, if the number of elements are really more, you should be able to use 32,32 number of threads in within each block. Now let us go to number of blocks within a grid. Again, in this example, I am using 2,2, but in general, if the number of elements are more, you should be able to use this rather than 2,2, where n by block dimension in x direction and m, where m comma n denotes the number of rows and columns, and where m by block dimension by y, so which means those many number of blocks you are declaring in y direction. Yeah. So once you declare appropriate number of threads, now the next one is the kernel launch. This kernel launch you are aware of, but one minor difference between this program and the programs what we have seen earlier was, here I am not passing the actual data. Global memory, earlier if you look at your earlier programs or the first day program, they're using CUDA ML lock and using CUDA mem copy, using those functions, right? Using those functions, we have copied data explicitly from global memory, from host memory to from CPU to GPU, and also we have dynamically created memory using CUDA ML lock. That is of course the best way to do, but here there is one more an easiest mechanism I'm teaching in this session, where you look at this syntax. This syntax is very powerful in the sense, within a device, which means in GPU, we are going to declare this two-dimensional array. So which means now you don't have to use any CUDA ML lock. This is the simplest mechanism if at all you know the total number of elements. But in many cases, since static memory allocation is not so efficient, we go for dynamic memory allocation. But few programs, when you are in the beginning, you should be able to use this kind of syntaxes to declare some static GPU, some 2D arrays in GPU memory, in global memory. Well, now which means this global memory, you have declared before the main program. So which means these variables you can directly access in your kernels, in kernel definition. So you are not going to pass these parameters as a parameters within this kernel function. Otherwise, typically we were doing that in our earlier programs. Now let us come to the main the kernel definition. In the kernel definition, you know how to obtain the column number of a particular thread and row number of a particular thread, right? Once you know that, again you have seen this the column value should be less than n minus 1 and less than m minus 1. This conditions we typically use to avoid computation for passive threads, right? We have discussed this point at some time, where there are sometimes where the number of threads what we create could be more than the number of threads what we really require. So in such cases, the other passive threads should not do anything. For that reason, we are using this condition explicitly. And further, finally, we are using this go to particular element and increment accordingly. So fine, well done, right? Yeah. So this program works perfectly fine, but we have to understand how are we copying the data. So here is where host array has been declared in two-dimensional fashion. Again, device array is also declared without using any dynamic memory allocation. We are declaring using static memory allocation. Directly we are fixing these numbers. Now this is the main function that I want to refer here in this slide. CUDA mem copy to symbol and from symbol, right? Earlier we have used CUDA mem copy directly. Such functions are useful to copy data from global memory, from CPU memory to global memory, when the GPU variables have been declared using dynamic memory allocation. So which means they are just pointers. Whereas in static memory allocation, when you do, these kind of variables, in some sense, people call them as the symbols. That is the reason we are explicitly saying now CUDA memcopy to symbol, right, from host memory to device memory. And since this data is already declared under global scope before main program, we are not passing those parameters. If at all you need m and n, all some other parameters you can always pass based on your requirement. Finally, once the kernel launch is over, once the kernel is completely executed, your result will be finally available in DA, right? That's what we have seen earlier, right? Your final result is available in DA array, and now you have to copy back that result to A. That's what you are again doing from DA to A using the from symbol, CUDA mem copy from symbol. You are getting back the data, of course, the required number of bytes. So hopefully this program is clear. This is just an addition, some increment version for one-dimensional array. Now let us go to the core concept of today's session, where we are discussing about this thread divergence. If you recall your previous session, if at all there is a block which consisting of 100 threads, internally all these threads are grouped together as a 32 threads, right? And this first 32 threads, 0 to 31, T0, T1, T2, so on, T31, these 32 threads we are calling as a warp 0, and the next warp, and so on, and the rest of the threads in the last warp. How these warps are going to perform memory allocation, memory accesses, we have seen last time. Today's session is about computation. This is very much interesting, and please pay attention here. There is one programming question which we are going to see today. If at all you are looking at solution for this programming question for the first time, definitely you will be able to get this aha moment, right? Please pay attention, and we'll be able to enjoy this aha moment based on the solution what we are going to look at based on this thread divergence. Yeah, keep listening. So here is the mechanism of warps. So here internally you have, I mean, it depends on certain kinds of multiprocessors. I'm talking about one streaming multiprocessor. Within one streaming multiprocessor, we have two warp schedulers. Within each warp scheduler, we have within each warp we have here you have 32 threads. Here also you have 32 threads. So total you have 64 number of cores. 64 number of cores are available in one single streaming multiprocessor. If that is the case, then at a time two warps can be scheduled. At a time 64 threads can be scheduled, right? Typically, I mean, I have answered this many times. Is there a one-to-one mapping between the software view, the number of threads what we launch, and the number of cores that are available in your GPU card? Of course, there is no limitation. In the hardware, there is a limitation. Maybe some 64 cores are available in one SM. It doesn't mean that you have to within a block. I mean, blocks are taken care by streaming multiprocessors. So, which means you are not supposed to worry that, oh, I should able to create only 64 threads in one block. No, we encourage to create more number of threads within a single block, because when one warp is being executed, within a warp we have some kind of computation kind of instructions, right? And there are memory access kind of instructions. Computation kind of instructions are typically faster, whereas memory access kind of instructions, which means loading and storing, it requires some time. In such time, the actual cores will be idle, right? So which means some amount of time, if you want to hide such kind of latencies, right? If you want to hide such kind of latencies, you better have more number of warps within a single block. So which means though you have only two warps that can run simultaneously, but if you have many more warps, all of them start fetching the appropriate bytes from global memory and so on. So always it is encouraged. And of course, if you try to understand where each walk can work potentially on different instruction, this we are going to discuss in detail in the couple of slides, in the next couple of slides. So this is one of the fundamental difference between CPU threads and GPU threads. You look at multi-core programming, you must have seen where if there are a lot of instructions and you launch multiple threads, right? T0 thread can be running, T0 thread might be executing instruction 1 and the T1 thread might be executing instruction 3. That is quite possible because we have multiple threads and all these multiple threads are executing the instructions completely independently, right? Completely, all the threads are running the same code, of course the same code, but all of them are executing independently. There is no much more synchronization unless as a programmer explicitly mentioned. Whereas in GPU threads, these are 32 threads. These 32 threads I am calling as a walk. The threads which are available in single walk, always they try to guarantee to execute the same instruction at same time, and such kind of execution people usually refer to as a lockstep execution. So which means all these 32 threads finish executing the first instruction, then again all these 32 threads again come to execute the second instruction, again further the same 32 threads will go and execute instruction 3, and so on and so on and so on. This is how we are executing this the concept of single instruction multiple data. So which means a single on the same instruction is being executed on multiple data by different number of multiple threads. So here there is a single catch. If you are paying very serious attention, you should be getting some natural doubt. So do you think that always these threads, say 32 threads, are going to execute the same instruction? That's the intention. That's the intention when people develop this hardware. But always does this happen? Or based on the kind of program that we write, based on the developer, sometimes there is a possibility that these 32 threads will have some kind of distraction. Right? If you pay attention, possibly you must have got some answer, and otherwise you can listen to the next slide. Right? We as a walk we have 32 threads. As of now in this example, you think of 8 threads: T0, T1, T2, and so on, T7. All these 8 threads are executing all these S0, S1, S2, S4. All these instructions we are executing one by one. That's the intention. Now let us go and try to see what happens. The first statement, this is S0. S0 is very clear. We are just, what is the purpose of S0? It is just to identify my own index value based on this expression. Every thread is going to identify what is my thread ID number. Absolutely fine. Next statement, what is that? There is a if condition. Based on this if condition, whether it is true or false, right? I mean, this I'm calling as statement 1, not the if condition. This assignment I'm calling as a statement 1, and this assignment I'm calling as statement 2. The same threads, right? We have 32 threads or 8 threads. They're going to execute all these instructions one by one. And for some threads, the if condition is true. The if condition is evaluated to true for some threads. What happens to other threads? For other threads, the if condition is evaluated to false. Then what happens? There is a if body and else body, and some threads wanted to execute the code sitting in if body. There are other threads which wanted to execute the instructions available in else body. So now such kind of scenario where both of them, these 32 threads, are kind of very, very close friends. Wherever they go, they are going together. But this is the place where there is a kind of divergence is happening because of this if else condition, right? So when this divergence happen, few threads are going to execute S1 statement. When S1 statement is being executed by 4 threads, the rest of the 4 threads are not going to execute any instruction. They are supposed to sit no operation. They're just being idle till the other 4 threads are finishing the S1 statement. I mean, of course, in this example, since we are talking about only 8 threads, we are discussing like this. But in general, in 32 threads, few threads might, for few, it depends on what you write in the if condition, few threads can go to if block and a few threads can go to else block. Now what happens when few threads are executing S1, the rest of the threads are executing no operation instruction. So which means they're setting idle. Again, after this time is over, then in the next time unit, right? Then in the next time unit, the other instructions, the other threads which have been idle in the earlier time, those threads should execute S2, and the earlier threads need to sit idle in the current. So which means though there is a potential to execute all these instructions in parallel by multiple threads, but because of they're all working together in a single warp based on the kind of mechanism the GPU is supporting for us, due to this mechanism we call SIMT, single instruction multiple thread. I mean, though the philosophy is single instruction multiple data, but GPU programming is not pure SIMD. This is SIMT, right? Because multiple, I mean, it is not strictly following the same instruction is not being executed on multiple data, right? I mean, there is a divergence is happening. Because of that, we call single instruction on multiple by multiple threads, and divergence is always happening based on your if-else conditions. So this is how the main execution is going to happen. But what is the lesson from this? The main lesson from this is when you write if-else condition, you have to be very careful, because the number of time units here are increased by 1, because this is when if block is executing, some threads are idle, and when else block is executing, the other threads are waiting. So because of one if else condition, this kind of branching is called two-way branching. This kind of branching is called two-way branching. But you think of nested if else. Suppose if you write something like this, if else, and within this if again you write if else, within this else again you write if else. If you write this kind of code, then there is a four-way branching takes place. Possibly you can spend some time on this. So what I'm essentially trying to say is, depends on your if else conditions or switch statement, there is a divergence is happening, and you should try to reduce this. If there is a lot of divergence, then the amount of the number of time units it is going to take for executing will be increasing. So you should pay attention and try to decrease the thread divergence. That is the main lesson. Yeah. Now let us go and discuss few more examples. You look at this kernel 1. In the kernel 1, we are discussing about based on some condition, either statement 1 or statement 2 is going to be executed, right? Earlier, what did we see? We noticed that conditions are bad. That's what we have seen. But is it correct? We try to understand the same. Conditions are not always bad. Conditions are fine. You can write conditions in your GPU programs. It is not at all bad. But you have to be careful that, is this condition true or false? Please verify this n and vector size or values or certain values which are common for all the threads. If this condition is true, suppose true for T0, suppose true for T0, what happens? For T1 also the condition will be true, and for all the threads this condition is true. For all the conditions, for all the threads, this condition is true, which means writing conditions is not a bad idea, right? What do you understand? If few threads are going to execute if statement and few threads are going to execute else statement, then that is considered to be bad. So which means as long as all threads evaluate to same truth value, it's perfectly fine. There is no divergence. Though there is a conditional statement, the threads are not doing any divergence because of this kind of conditions. Now, what do we understand from this example? If threads are evaluating to same truth value, it's not problem. But if threads evaluate to different values, right? If threads evaluate to different values, then there is a possible problem. We'll understand that. So in this example, let us understand again the conditional statement. What is this TID value? TID value could be either 0, 1, 2, so on, 31 or 32 and so on. Right? This is 0, this is 1, so on, this is 31, this is 32 and so on. What happens now? You look at for all these threads. For all these threads, the condition is evaluated to false. This thread value is something like 25. 25 by 35. This value will be 25 by 35 value will be 0. So it is false. So for all these threads, the truth value will be false. So all these threads are going to execute this statement. All these threads are going to execute this statement. So can we say there is a thread divergence is happening? No, there is no divergence. Divergence is happening across warps. Absolutely fine. There is no problem. What did we discuss earlier? Within a warp, the 32 threads, when they are going to execute the same instruction based on this if-else condition, within 32 threads, if some threads want to divert to one statement, another threads wanted to divert to else statement, that is called thread divergence. So here that is not happening. So this is also absolutely fine. There is no problem. Then what is the lesson now? Threads within a warp, within one single warp, if threads evaluate to different value, that we call as a thread divergence. And we should be able to reduce such kind of divergence. So we look at one more programming question. This is what I referred in the beginning. This is a very important programming question. Today we are going to spend a lot of time on this question and subsequently the solution. We have these n number of elements are there in a array, right? What do we need to discuss? We need to just compute the summation of all these numbers. Some 6 minus 7 8 12. Some of these some elements are given for us. An array of n numbers are given for us as an input. Now what is the programming question? We need to just compute, just perform the summation of all these elements. Finally you give me one single value. This is the programming question. Hope you are very clear with this. Think of parallel algorithm. You know, sequential algorithm is very well known. Or take the first element, take the second element, keep the summation in your sum variable, keep on going to the subsequent elements. Take the next element, you have your sum variable, sum is equal to sum plus the current element. Go to the next element, you already have partial sum is available. You take the new element and add to your existing sum variable. Sum is equal to sum is incremented by the current value. Again you go to fifth element, sum is incremented by a of 5. Again you go to sixth element, sum is incremented by a of 6. This is very common, very natural program you must have executed in using the C programming or any other language in the serial setting. Now we want to discuss a parallel algorithm. For this, of course, there is a non-trivial algorithm available. We are going to discuss this parallel algorithm. Yeah. So using this example, we try to understand the parallel algorithm, and then later we discuss about the implementation. The algorithm itself is very interesting. On top of that, implementation is very beautiful. Yeah, let us discuss this algorithm using this picture. The first two elements, we perform summation and put it here. Next two elements, right, we perform the summation and put it here. The next two elements, we perform the summation on both of them and put it here. the final two elements, we do the summation 24 and 6 and get the value and put it in here. Now what is the parallelism that we can afford here? When these two elements are being added, these two elements also can be added, and these two elements also can be added, and these two elements also can be added at same time. At same time, that is what we are thinking of parallelism. So which means all these four elements, right, this 40, 29, 35 and 30 can be obtained in one single step. Within one step, right, within one step you are able to reduce from these 8 elements to 4 elements. We have already performed these summations. From these 4 elements, again you are doing this pairwise summation, right? When you do this pairwise summation, these two elements you are doing summation and able to get here. Again, these two elements you are doing summation and put it here. So all that again you can do in parallel. When this summation is happening, this summation is also happening in parallel. So again, within the next iteration, within first iteration, we call them as phases or iterations. Within first phase, 8 elements have been reduced to 4, and in the second iteration, 4 elements have been reduced to 2, and in the third iteration, 4 elements have been reduced to 2, and hence the total number of iterations or phases will be 3. And in general, when you have n elements, the number of phases will be log n base 2. And so in some sense, people say that running time of this algorithm is order of log n and so on, right? Yeah. So here, this algorithm is very clear. Now you all have been familiar with some of these parallel programming frameworks, maybe OpenMP or MPI or even CUDA. We'll take break for a couple of minutes if you have any questions. Meanwhile, when I'm going to discuss these questions, others can think about how could we write the parallel implementation, the actual code. What is one-to-one mapping? How do we copy arrays? How do we handle these many elements? What is parallelism? All that as an algorithm we have discussed. As an implementation, we are going to discuss after a break. Yeah. So we are taking a break for a couple of minutes. Yeah. Shirayu, please.
Right. Hello, sir.
Yes.
I'm audible.
Yes.
Sir, so in the previous slide, can you go to the previous slide where in the very initial, right? Previous. When we are declaring this multiple dimensional increment, multiple dimensional array increment. Yeah, in this program, in the previous slide there, the question was why we were not declaring m and n variables.
Yeah,
Probably,
we have declared that. We have declared m and n variables here also. Of course, you have to declare. You have to declare somewhere in your whole program. It depends on where you declare, and you have to declare that.
Right. Sir, one student has a doubt that could you please explain the concept of warp again?
Okay. Warp is collection of 32 threads. Yeah.
Warp with the condition, the divergence, that part. That part could you? Yes.
Okay. So here you can think of, this is one example where you can think of say what happens to T0. What happens to T0 when T0 is executed? This if condition is a true or false. 0 mod 2, right? So 0 mod 2 is a 0 is an even number, and when you get 0 mod 2, you get 0. Then whether this statement is true or false. This statement is false. So which means thread 0 is going to execute S2 statement, because it is false. Because the if condition is false, the thread is going the T0 thread is going to execute S2 statement, which is nothing but else statement. Similarly, you look at T1. T1 is going to execute S1 block, and again T2 is going to execute the other block, and so on, right? Essentially here we are saying that all these 8 threads, right, some of them are executing S1 if block, and some of the threads are going to execute else block. So if that happens, then what is the running time, right? You are taking two steps, right? If this if condition, if this if else condition is not there, typically if there is a single statement and all the threads can execute that single statement within 1 unit of time. So, but because of this thread divergence, the 32 threads within a warp wanted to execute the single instruction on multiple data items in one single time unit. But because of this if else condition, they are diverging. This is fine. Yeah.
Right.
But
Right.
what is the main lesson? But what is the main lesson where we try to avoid this thread divergence?
Right. Right. So, sir, another student was asking that why do other threads have to wait? Why can't S1 and S2 happen in parallel? Means why can't it happen together?
Very nice. Very nice. So this is, I mean, the way GPU have been designed, the 32 threads wanted to execute the single instruction, a single instruction, right? Not multiple instructions. The 32 threads wanted to execute only single instruction, and they do not have power to execute multiple different instructions. If you are following that, then it is like a CPU mechanism. In CPU mechanism, thread 0 is executing some instruction, ith instruction, and another thread can execute potentially the another instruction. So which means then we are not following this single instruction multiple data kind of paradigm. That paradigm has been very popular in GPUs. That is the main reason where, if at all there are some problems where it's single instruction on multiple data we want to perform, then you don't have to fetch a lot of instructions. There is a lot of disadvantages there in GPU, because you are going to get only one instruction you are going to fetch, but working on a lot of data items, so you get that advantage. So by design in GPUs, we try to allow within 32 threads, we don't have a mechanism to execute different instructions by default, unless there is a explicit this kind of divergence happens. By design, we do not do that. If at all we want to do that, then the GPU also will become very costlier, in a sense where it is not going to be lightweight thread. Then these threads will be very similar to CPU threads. Then you'll not be able to execute single instruction on multiple data. Yeah.
Right. Sir, so the next question is, if we have a program, a function, which
Right.
we want to execute in multi-core. So I want to
Right.
launch in multi-core, and internally the function, we are calling some
Right.
GPU kernel.
Okay.
So
Okay.
is it possible to code like that?
Very nice. Of course, I have not tried. There is a possibility. Definitely, there is a possibility. But what I believe is something like within the OpenMP call. I mean, multi-core programming is absolutely fine. I mean, when you talk about multi-core programming, P threads, right? When you look at that level, right, then a lot of threads can start executing all this. At some point of time, you can have GPU kernels. That is perfectly fine. So which means then that task will be executed by GPU. That's perfectly fine. But whereas within a OpenMP function, right, when you write this parallel reason and so on in OpenMP, within that, if you execute GPU code, that's very tricky. I'm not sure about that. One should execute and see whether what are the weird results that you can get. But other than that, you can always multi-core and GPU is always perfectly good combination.
Right. Sir, so the next question is, what will happen if thread diverge?
Hmm. What happens when thread diverge?
What when thread diverge? Right. Yes.
Okay, that's what we have discussed. When threads diverge, then the amount of time it is going to take more, because when say within a 32 threads in a warp, when 16 threads are executing one instruction, other 16 threads are just idle, right? Say think of this scenario where there are as a group of 32 close friends wanted to go somewhere and wanted to do all of them some kind of task or shopping in the same room. Of course, then it's quite possible. But if all of them wanted to do in different places, or wanted to do different kind of tasks, then when someone is doing, others are waiting. They are not going to do anything. right? When these people are doing some task, the other people are just sitting idle. And again, when other people are doing something, the first set of people are being idle. Then which means the kind you are not effectively utilizing the parallelism.
Right, sir. The following question is that is thread divergence and warp divergence the same thing, or is it something different?
Yeah, it's same. I'm calling the same thing. Warp. I mean, within a warp, threads are diverging, and this concept we are calling as thread divergence or branch divergence. There is nothing like a warp divergence.
Okay, sir. The first question where I was asking about M and N are not declared, the
Right.
person meant that M and N did not have any value; they were not defined in the previous slide.
No. That slide is meant for only as an example, right? I'm just referring as an example. You can of course read M value, N value, assign all that you should be able to do. I'm just giving an as example where fixed values I'm giving as a program, but if those values are variables, you have to read, you have to do all that. All the codes, whatever I'm showing you, are not complete in nature. There are some partial codes. I'm explaining the major logic, but not the complete all statements. I'm purposefully not putting all of them. Then it will become very cumbersome in a slide.
Right, sir. All these are the questions, sir.
Very good. Yeah. Very good. So far, yeah. So hopefully some of you must have spent some time in thinking about what is the good parallel implementation, particularly CUDA implementation for this algorithm. We are going to see a nice implementation. On top of that, stay tuned that there are some limitations in the first approach. And to overcome this limitation, we are going to see the wonderful, really wonderful algorithm if you're listening for the first time. So please stay tuned for this. So this is the first parallel implementation. So of course, whatever we have seen in this slide, the same algorithm what we are looking at here, we are thinking in terms of implementation. So we are slightly, the picture is different and example is different, but the algorithm is same, essentially same. What did we do? The first two elements need to perform summation on the first two elements, and the final summation, the 10 and 1, the value will be 11, need to be stored in the first element. How many threads are doing this job? One thread is responsible to take the summation of the first two elements and put the resultant value in the first location or 0th location. Now at the same time, what is happening? The second thread, this is called 0th thread. Now we talk about second thread. The thread T2 is going to access A2 location and A3 location and do the summation. 8 plus minus 1 7 is going to be written in second location in the same array. This is fantastic, right? Similarly, we do the same kind of operation for every two subsequent elements, right? When two elements are being processed, how many number of threads? I mean, in the total we have n is equal to 16 number of elements are there in this example, and how many threads are active and how many number of threads are passive. So we are going to launch of course that depends on your program. Typically we assume that the number of elements are 16, and hence we launch 16 number of threads, and even threads, right? 0 2 4 6 even threads have some work, where odd threads, right? T1 T3 T5, they do not have any work. They'll simply sit idle. That's fine for the time being. So what are we going to do in in the first iteration? All these 16 elements pairwise we have added, and the final results are available in as here, here, and so on, right? So finally we have some 8 useful elements are available in the same array. This we are calling as step 1, and we are calling as stride 1 here because each thread is going to access its neighbor, its immediate neighbor. This thread is going to access the current element as well as its immediate neighbor in the right side. So that we are calling as stride 1. All this in phase 1. Now let us go to phase 2. This is phase 2. It is interesting. What happens in phase 2? In phase 2, this 11 needs to be added with this 7. So this element and this element are being added by thread 0 and put the result 18 in 0th location. Let us see this. Right? All this. All this happened in 1 unit of time. 11 plus 7 is equal to 18 has been written in 0th location by 0th thread. At the same time, what is happening? At the same time, what is happening with other elements? This minus 2 and this 8 are also being added, and the final result is 6. This minus 2, right? Pay attention. This minus 2, this 8 are being added, and the value will be 6, will be stored here in 4th location by 4th thread. So what are we doing here? Here also again we are discussing about very similar stuff, where pairwise elements, here the number of elements is the actual active elements here is 8. Rest of the elements we don't have to worry about. Only those active elements, again pairwise, they are getting performing this summation and adding into and copying into appropriate locations. So now how many number of threads are active? In this phase, the number of threads that are active is 4. And where are they going to access the elements? You look at the 0th thread. 0th thread is going to access the 0th element. Pay attention a little more on this. 0th thread is going to access an element from 0th location and another element from by 2 elements away from the current element. Similarly, you notice this. 4th thread is going to access the location, the element available in 4th position, and another element which is away by 2 locations. Earlier it was away by 1 location. In the second phase, the ith thread is going to access an ith element and another element which is away by 2 elements. You look at the next phase. In the next phase, again ith thread is going to access an ith element and an element away by 4 elements, and finally in the final iteration, ith thread is going to access ith element, meaning the corresponding element. And what is the corresponding pair? The pair will be away by 8 locations. This is the major the implementation detail. Now once you understand this, now we should be able to go for the actual code. So now what is the code? So if you look at in the previous slide, we have seen that every thread is going to access only 2 elements. This is that simple job. Of course, it looks so complicated that lot of threads are working, reading, doing computation, writing. But what is the task for each thread? Each thread is going to simply take 2 elements, do the addition, right? Perform the summation and put the result in the first location, right? They're accessing 2 locations and kept the result in the first location. Now what is happening in the first phase? Because as we discussed in the earlier slide, in the first phase or in the step 1, the ith thread is going to access an ith element and another element which is available away by 1 position. Whereas in the second step, it is going to access another element which is away by 2 locations, away by 4 locations, and away by 8 locations, that we are calling as, in some sense, either you call as offset or stride, whatever you give that name. But we should able to increment that. Earlier in the first phase, this value should be 1. In the second phase, that value should be 2. And third phase, 4 and 8. Since we have worked on 16 elements, we got 4 iterations. This is one important observation you have to make to understand the code. And what is the another important observation? In the first phase, only even threads 0, 2, 4 are active. In the second iteration, not all even threads, only the threads which are multiples of 4 are active. In the third iteration, multiples of 8 and further 16. This is the major These are the major observations. Based on this, we'll try to see the code, the actual implementation. This code, you look at where this you write in the within a main. We are going to write this program, and this is going to be your kernel definition. Whenever you see this kernel launch, we go and execute in GPU. So which means GPU kernel call will be called for 4 times, right? First step 1, right? Whenever we do all this computation, we are doing in GPU and come to this phase. Again in CPU, one more function call is made, and all this computation is going to be happening, and final result is available in GPU. Again, keep on doing this, right? So there is some sequentiality is happening, so that we are doing in CPU. And whenever you see that there is a kernel launch, all this is being executed in GPU. In GPU, what is the main code? This is such a simple program. If you look at very carefully, right? Each thread is going to just take 2 elements and do the summation and put the result in EFI. That's simple, right? But when you look at all these multiple threads, their coordination, it's tricky. So then what is the other important concept here? The stride value is multiplied by 2 every time, right? That's what we have seen in earlier also. This is going to be 1, 2, 4, 8. So in the very beginning, this stride value will be 1, where this value will be 1. When you launch the same kernel multiple times subsequently, by that time this will be 2, 4, 8, and so on. The values have been incremented. Then there is another important statement in this whole code, this one, where all the threads are not supposed to compute this. Only few threads. In the first iteration, only even threads, right? There is a relation between this and this. When this value is 1, this should be even. When this value is 2, when the current thread is working on the elements which are away by 2 positions, right? Then here it should be multiple of 4. When this value is 4, this value is multiple of 8. So this stride, here it is 2 times stride. This is stride, and this is nothing but 2 times stride. That's what we are seeing here. When I is a multiple of 2 times stride or not, that's what we are doing just in this if condition and executing the statements accordingly. Whole program is over. Now it is your turn to think about, is there any limitation or is there any drawback in this program? Of course, there are many drawbacks, but what are the major drawbacks? If you pay attention, there are few drawbacks which we are going to list here. Of course, not by looking at the code and internals, by looking at the example itself, right? By looking at the example itself, we should be able to understand what are the main drawbacks, and based on this, we should be able to go for this the so-called AHA algorithm, what I just pronounced in the beginning. We are going to discuss the beautiful algorithm, which we call so elegant. You are going to look at the richness of this once you understand the drawbacks of the current algorithm. What are the drawbacks? What I see are few which are listed here. Underutilization of threads. When we launch 16 threads, right, here we have 16 elements and we are launching 16 threads, but only few threads are active, other threads are passive. So which means threads are not being utilized properly. Of course, if you can write little more slightly differently here and there, you can try to resolve this, but you have to pay attention that the thread divergence is also happening here. What do you mean by that? When even threads are working on this, there is another thread here. That thread is just sitting idle because of your if condition, right? Because of this if condition, when some threads are executing this, other threads are sitting idle, right? And then other threads are executing something, which means that other threads do not have anything, but still because of this if condition, there is a thread divergence. So this thread divergence we would not like to have. And there is one more drawback, which is the most important drawback, which we are calling as memory transactions. What does that mean? You are going to, you look at this somewhere here, somewhere in this phase. Actually you want to work on only this element and this element, right? But when you are working on this, you are going to fetch all the other elements, because you are transacting the transactions, or in terms of chunks of memory locations, the other elements are also being transferred, but they are not going to be useful. This, I would say, one of the most important drawback for this example. So now let us go back and try to resolve them. And this is what I'm referring to as this AHA algorithm. And this technique is called reduction technique. Of course, the previous algorithm is also comes under reduction technique, but earlier we have all these problems, thread divergence, memory coalescing is not better and all. But in this current algorithm, what we are discussing, all are beautiful. Right? In a sense, there is thread divergence, of course, is there, but this is very minimal. We'll come to know that. And memory transactions are also minimized. We'll go and discuss all of them in detail. We are going to discuss this now. Now let us, if you look at in the very first iteration, the total number of elements are 16. But how many number of threads you are launching? We are going to launch only 8 threads. This we call first part. This we call, right, the first 8 elements we call first part. The other 8 elements we call second part. We are dividing the whole, all of the elements into 2 parts. Threads are working only on the first part. Threads are working on first part. On the same threads, these threads, right, say thread 0, this is T0, is going to access one element from first part, the other element from second part, the other element from second part. Similarly, the thread 1 is going to access one element from first part, right? This is the first part. What is the other element? This thread is going to retrieve the another element from the ninth location. So which means again we are going to look at every thread is going to access 2 elements. But what is happening? If you look at this, right, the elements are, if you look at the each thread is going to access one element from the corresponding location, and other element is away by 8 elements. Other element is away by 8 elements in the first step. Now you see that after this iteration is over, all your important values are available here, and all these values, which is nothing but all these values, are not at all required, because all the elements from the second part have been added to the first part in the corresponding places. So which means your second part completely you can eliminate, and you don't have to touch those elements anymore. So which means whatever you are accessing, you are going to use all of them. And from your second iteration onwards, this is your first iteration. In the second iteration, all these elements you are not at all going to touch. So which means your memory coalescing, I mean, whatever are useful, you are transferring them or touching them or accessing them, but unuseful, right? Not going to be useful. Such kind of elements you are not at all touching. That's one of the primary point. And further, even if you look at thread divergence, right, what happens? Do you see any passive threads here? There is nothing like passive threads. Whereas in the previous example, there are a lot of these passive threads, right? Because of these passive threads and active threads, there is some minimal thread divergence is there. But whereas here, all the threads more or less are always active. Only these active threads we are launching, and these threads we do not even launch. So when you are working on 16 elements, we launch only 8 threads. We launch only 8 threads, and they are going to access ith element and another element which is away by 8 positions. This is the main idea. So once you obtain the summation of these elements and these elements and put the corresponding summation here, then what do? You continue again. Now you have 8 elements are active. You launch only 4 threads. These 4 threads are going to work on. Again, you can divide them into 2 parts, and these 4 threads are going to work on the first part and second part within this. and put the final result here. Similarly, you keep on doing this. Finally, you will be ending up your final result in the very first location or 0th location. Now, if at all you want to look at the code, before you look at the code, we need to have some observations. What are these observations? Observations are written down here. Earlier, we have something like, you look at this, right? You look at this line. The stride is being multiplied by 2 every time. Earlier, away by 1 element, away by 2 elements, away by 4 elements, and so on. Whereas that is completely reversed in some sense in the current algorithm. In the very beginning, we start retrieving some element by 8 elements away from my current element. Later in the next phase, only by 4 elements, because the other elements are completely passive. We don't have to even touch them, right? This is what happening. So which means ith thread is going to access ith element and away by 4 elements, away by 2 elements in the next iteration, and away by 1 element. This is in the final iteration. So now what is the advantage? We have seen that the other elements are not at all even accessed, and only threads which are relevant are active. So there is nothing like a passive thread. So which means thread divergence. If you talk at a little superficial, we can say that there is no thread divergence at all. But if you look at little more in detail, there is a small thread divergence is there. That is because of one of the one of the core reason that at some point of time when you go and execute all of them, there are only two threads here, only 4 threads here. There is only one thread here, right? When you do this, typically when you launch, I mean, this is an important point. When you launch one block on 32 threads, right? Or maybe this is not even 32. One block, maybe 5 threads. When you do this, right? When you launch only one block and 5 threads, what happens? You want to launch only 5 threads. That's perfectly fine. Logically, even if you print the ID numbers, you will be launching only 5 threads. But internally, because we are following this warp kind of mechanism, 32 threads have been launched internally by the hardware. Of course, for the programmer, there is no worry in a sense where you will be getting output for only those 5 threads. The other threads are not even, you cannot even access the thread IDs for the other threads because the programmer did not launch them. So you cannot even access the thread ID for other threads. But because the hardware is actually going to work on only 32 threads at a time, the other threads are being underutilized, and also some kind of thread divergence is happening because of the other thread. So people usually refer that as a very minimal thread divergence. So now this is perfectly fine. This code we are going to look at. Yeah, please pay attention to this code and try to understand what are the major differences. Of course, now also you see that EFI is equal to EFI plus stride, because every thread is going to just access only 2 elements and do the summation, right? But there are certain changes where stride value is initialized with n by 2 and keep on reducing by 2 every time. That's what we have seen here, right? Earlier it was 8, then 4, then 2, and 1. Whereas in the earlier example, we started with 1, 2, 4, 8, and so on. So that is one of the major difference between these two codes. Earlier we started with we started with 1, then 2, 4, and so on. So stride value was incremented by 2, multiplied by 2 every time. In the current code, stride value is divided by 2 every time. This is one of the major difference. This is one of the major difference. And another difference is also where n value is the total number of elements have also been reduced by 2 every time, because we have seen that all these elements are not going to be useful in the next iteration, and hence we only launch, we need only n elements. N is divided by 2 every time. Of course, other than this and this statement, there are other statements in the code that you should be able to spend some time and be able to understand with some minimal time and effort. I'm not going to discuss those. But there are certain important conditions, this and this. I'm going to spend time on that because kernel call is most important, and CPU code you should be able to understand if you spend some more time. Yeah, so here we pay more attention why we are writing these two conditions. Though it looks like one single instruction or code, but it has a lot of impact. Let us look at these examples and try to understand. The number of elements, let us assume we have 2050 number of elements are there. What does it mean? A0, A1 and so on, A 2049, right? These many number of elements we have. Let us assume we have these many number of elements. Then how many threads we have? We have to launch 1025 threads because this is the first part, second part. Only first part is responsible to take care of the second part also. So the number of threads are half of the number of elements. So which means 102425 threads, and also stride also, you know, of course, right? If the number of threads are 1025, how many blocks we have to create? Number of blocks will be 2, right? So which means your first block 1024 all are active. Now you look at your second block. In the second block, because you need 1025, we have created this second block. In the second block, only one thread is active and all the threads are passive. They do not have any job even in this current algorithm as well. Right? So which means all these threads are completely waste in some sense, and we have to be very careful that these threads should not touch any memory location. So how did we do that? In the earlier programs also we have written somewhere, if I is less than n, go and do some task. Exactly same as that, right? Same as the same logic we have written where I value is less than stride. Right? What is the stride value here? 1025. So what is this thread ID? This is 1024. This 1024 is less than stride, which means it is active. This thread, what is the ID? 1025. Is it less than stride? This is equal to stride. So which means the if condition is false, and all these threads do not execute this code. That is what our intention. So that is the reason we have written this if condition, where there are certain threads which are passive, and those threads we do not want them to touch any memory location. That is the reason for this condition. There is another condition which is very much important. This condition is responsible for not having a partner. In the example what we have seen, n value was 60. So then you do not have any problem, because it is even number. If n value is 17 or something, which is the odd number, then you do not have a partner. So which means this is your first part, this is your second part. In the first part we have these many number of elements, including 8. We have 9 elements. Now you look at the partner, right? Some thread is going to retrieve this location and this location, which is stride away by 9. Then this element again has a partner, whereas this element, right, do not have any partner. So we have to be careful for that. So whenever a thread is being launched on that element, we have to be again careful that when you add this stride value, right, when you add this stride value, you'll be going to access this memory location, which is not at all there. So which means you should not touch that. So as long as this thread value is less than n, you better access, otherwise you should not. That's the main lesson here. So which means now we have discussed about the complete lower level details of these two as well. We almost we are almost in finishing today's presentation. This is the last topic today. This is about atomic add instructions. You must have understood about atomic operations from your previous modules. If at all you want to increment the same variable by multiple threads, what happens? This is the programming question that you can think of. There are a lot of numbers are given in an array. we want to find out the total number of even numbers. You just go and access all these elements. If it is an even number, you increment a counter. If it is an odd number, you are not going to increment any variable. So what is the main code that we write? Of course, some number of some piece of code you write. I'm focusing on the main code. The main code is this. If the element is even number, then d count plus plus. If you increment this variable by multiple threads, what happens? That's what we are going to discuss, right? So this is what happening. So earlier, let us assume the total number of even even number of elements what we have initialized. The d count value might be 0. In the very beginning, let us assume the d count value is 0, and this is t0 and this is t1, and this is going to read some element called 2, and this is going to read some element called 8, and both are even numbers. This t0 and t1, right? This t0 and t1, both of them wanted to increment the value 0 by 1. If both of them do in serial, there won't be any problem, but both of them doing in parallel is a problem. When both of them is doing in parallel, there is a chance that d count value need to be read into internal register. Both of them will be having internal registers. This is happening in assembly level language. We are not going to do all that, but when these two threads wanted to increment same value, what is happening? The d count value is stored to an internal register. The register value need to be incremented, and then again the register value needs to be copied into d count. This sequence of instructions are being executed by two threads in parallel. So what is happening? T0 is d count value, it is copied to R0, so which means R0 value is 0, and increment R0, so now R0 value will be 1. The same thing, right? The same thing is going to be happening. All this is being executed by T0. The same set of instructions are being executed by T1. Then what happens? T1 has its own internal register, say R1. So T0 d count is copied and incremented to R0, so which means R0 value is 1 for T0, right? So R0 value will be 1, and T1 has one more internal register called R1. That value also is going to be 1, and when both of them are going to write, and R0 and R1 by another thread are going to be written to d count. So finally you are not going to get the value 2 because of complete parallel operations. So in such cases, we use this syntax, atomic add, and the address of the variable increment by 1. If you use this syntax and use this atomic add instruction, then though multiple threads are going to access the same location, but increment operation, all these instructions will not be executed in a interleaving fashion. Rather, all these instructions will be something like all of them will be executed by T0, then by T1 completely. So if you use this atomic operations, you will not get any incorrect results. Finally, whatever your intention, you are trying to work out that intention, and finally you will be able to count the total number of even elements in the given array for this program. So this is the atomic add operation, and similarly we have atomic min, atomic max. Essentially, I'm saying that if multiple threads are going to perform the same operation, either add or min or max, some operation if it is going to perform, if all of them are updating in parallel, then there is a problem. In all such kind of scenarios, you better use this atomic add or atomic min or atomic max kind of operations, so that some sequential will happen, but still your program correctness will be maintained. So I'll end here. The summary is we have discussed about all these 4 kinds of major topics on today, and the corresponding programs. In handling arrays, we have seen how to increment elements. In thread divergence, we have seen this summation of elements in an array. Under atomic operations, we have seen how to count the total number of even elements. On CUDA functions, new syntaxes we have seen on the memcopy from symbol and to symbol. And finally, the whole theme is about how do we reduce the thread divergence. So we'll stop here and take some questions